So, without further ado, let's dive in and start covering the new material. This presentation is going to focus on sensory perceptions, both general senses and special senses. When we look at our senses, we can divide our sensory receptors into two broad categories. Both of these categories of sensory receptors are going to be involved with taking some kind of specialized stimuli, maybe temperature or pain, or maybe pressure or light or vibrational frequencies, and turning those stimuli into an electric signal that can be processed by our nervous system, more specifically an action potential. The two broad categories are exoreceptors and internal receptors. Our external receptors focus on special senses from the outside of our body. So what are we tasting? What are we hearing? What are we seeing? What are we smelling? And then our internal receptors are going to primarily be involved with maintaining homeostasis in our bodies. What does homeostasis mean again?
Your body's ability to maintain all of its functions.
Yeah, more or less. Our body's ability to maintain its functions, and as we're trying to maintain those functions, we want to keep the chemical environment inside of our body the same. We want to have a constant blood pressure, a constant body temperature, a constant blood pH, so on and so forth. Depending on the specific kind of signal that our sensors are picking up, we can categorize the sensor on the kind of signal as well. So we can categorize them based on where the signal is coming from, the external part of, or the internal environment. And we can also categorize them on the kind of signal it's transducing. So we have a chemoreceptor that focuses on a chemical monitoring, or some kind of chemical that's being monitored or perceived. A special kind of a chemoreceptor is going to be a nociceptor, or pain receptor. Good examples of a chemoreceptor would be ones that monitor the pH of our blood, or the partial oxygen concentration, or the pCO2 content of our blood. Those are common variables that are measured by chemoreceptors. We also have chemicals in our body that are used to signal pain. One such chemical is capsaicin, and one such receptor is stimulated by the chemical capsaicin. And when we stimulate a chemical receptor with capsaicin, it activates a nociceptor. Capsaicin is a chemical that's particularly famous for making peppers taste spicy. It's the spicy chemical. We also have a photoreceptor. These photoreceptors respond to light energy. And when you think of our photoreceptors, I want you to think of the rods and cones within the retina of our eye. They can take a photon of light and go from a photon to an action potential. We also have mechanoreceptors. These mechanoreceptors take some kind of a mechanical force and turn it to the action potential. So these are going to be our light touch receptors, our deep pressure receptors. These mechanoreceptors also can take vibrational waves and turn them into electrical signals. So think of a sound wave being turned into an action potential. That's done by the mechanoreceptors in our bodies. And then finally we have thermoreceptors. These are specialized nerve endings that change and respond to temperature fluctuations. Here, from your textbook, table 15.1, is a table that's great fodder for flashcards. For those of you who'd like making flashcards, we're going to talk about all the information on that table in more detail as we plow through this PowerPoint presentation. Now, if we look at our sensory receptors, they can all respond to some kind of environmental stimuli. That could be the external environment or our internal environment. They need to be able to respond to the stimulus. After they take that stimuli, whether it's a chemical, a mechanical, or a temperature-based stimuli, they need to take all of those stimuli and turn them into action potentials or nerve impulses. And those nerve impulses eventually work their way to the brain. They'll be rerouted to the brainstem, from the brainstem to the thalamus, and then from the thalamus they go to our parietal lobe within our brain. And the parietal lobe of the cerebral cortex is going to have the part of the brain that monitors most of our sensation. Think back to chapter 14's material when we talked about the central nervous system and the peripheral nervous system. What we had the the post-central gyrus that contained that primary somatosensory cortex. So that's the specific part of our cerebral cortex that processes most of our sensory reception. And then as we are exposed to sensation, eventually we become numb to the sensation. A couple of years ago, Febreze had a commercial or an advertising campaign that used the phrase nose blind. And the idea is that if you're constantly exposed to the same smell, eventually you do not smell that smell anymore. A good example is your own body odor. Most people don't smell their own body odor, but other people can smell your body odor no problem because they aren't exposed to your body odor constantly. Or other good examples would be a dirty room that stinks all the time. We have the ability to zone out or tune out repetitive or continuous stimuli because our body prioritizes and wants us to specifically focus on new or novel stimuli. Here's a good example. When you're sleeping at night, most of you can probably sleep with a fan running in the background, no problem. It probably even helps you sleep better at night having that fan running in the background. On the other hand, if we had a sink or a faucet dripping water, maybe once every 10 or 15 seconds with a loud bloop, bloop, once every 10 or 15 seconds, that would drive most people crazy. And the reason for that is that continuous stimulus from the fan gets zoned out. But that periodic, non-continuous stimulus from the sink is constantly going to be hyper-focused on because it's not regular or repetitive enough to be zoned out. Other examples include the clothes that you're wearing, or your earrings if you have earrings, or glasses. Eventually, you forget that you're wearing glasses. You just zone out and forget about and tune out those sensory perceptions. Regardless of whatever stimulus we're working with, all of those stimuli are going to stimulate some kind of specialized sensory receptor on our neuron. And those sensory receptors are then going to conduct information to the cell body across the dendrite or axon, also known as a nerve fiber. And from there, it is sent to the spinal cord. And from the spinal cord, it goes up to the brain, where we process that information. Many of our sensory neurons located in our peripheral nervous system are going to have part of their axons within the central nervous system. Part of their axons will typically terminate within the spinal cord or the brain stem. So, class, concept check. Which of the following mechanisms would trigger a chemoreceptor? We have an increase in body temp, a decrease in blood oxygen, pressing against your big toe, or if you spin a person in circle. Which of the following would trigger a chemoreceptor? A, B, C, or D? We have a B from Ashley. Alyssa, what do you think? B? Well, that is the correct answer. B. A decrease in blood oxygen would trigger a chemoreceptor. As the follow-up, we would have a thermoreceptor triggered by A, and then C and D would be a mechanoreceptor being triggered. Let's keep moving on and talk about proprioception. We have proprioceptors which aid us with proprioception. Proprioception is a technical term that refers to, for lack of a better term, coordination. People that have good coordination have good proprioception. People that have bad coordination have bad proprioception. I like to describe proprioception as knowing where your body is in space. So if we think about when people are classically or traditionally uncoordinated, there are two stages in life when people are really, really uncoordinated. When you're an infant and when you're a 11, 12, 13-year-old. Both of those stages in life are correlated with rapid growth spurts. And as a person is growing very quickly and changing height very quickly, their body's sense of orientation, knowing where your limbs and appendages are in space, that sense of proprioception becomes impaired. To aid us with our sense of proprioception, we have specific mechanoreceptors in our body. And these receptors are going to help us maintain muscle tone. They will help us to maintain muscle tension. They'll help us to maintain muscle stretch. And will help us know where we are in space. For example, we are going to have a muscle spindle receptor. And this muscle spindle receptor is a special kind of mechanoreceptor that measures how stretched out our muscles are. And it's one of the ways that you can know, even if your eyes are closed, if your finger is to the side, or know where your finger is in relationship to your nose, even with your eyes closed. Because you have these muscle spindle fibers that are subconsciously telling you how stretched out all of your muscles are. Another classic proprioceptor is the Golgi tendon organ. And our Golgi tendon organ is embedded inside of the tendon of all of our skeletal muscles. And it serves a very important purpose. It measures tension on the muscles. It's important to have some tension on our muscles, but we do not want too much tension. Particularly with the large muscles of the thighs and the buttocks, the gluteus maximus, the rectus femoris, the vastus lateralis. If we contracted those muscles with maximum force, many of us could rip the muscle off the bone. We could tear our tendons off the bone if we contracted uncontrollably. When individuals develop tetanus, oftentimes that's one of the side effects of tetanus, tearing tendon from the bone. This Golgi tendon organ, in addition to measuring the tension on the tendon, can also send a kill switch or a kill signal to our central nervous system. And it tells us to stop contracting the bone if there's too much tension on the tendon, if we're in danger of ripping our tendon from our bone. So, concept check. What kind of sensory receptors can send the most kind of sensory? I'm pretty sure we did not answer this one at all. I put that concept check in the wrong spot. Sorry about that, guys. Let's talk about some of our cutaneous receptors. If we look at these cutaneous receptors, some of our cutaneous receptors are going to be specialized for pain reception. Some of our cutaneous receptors will be for temperature, some for pressure, so on and so forth. Generally speaking, if the closer to the surface the sensory receptor is, the more focused that sensory receptor is going to be on light touch or more fine-tuned signals. The deeper in the skin our sensory receptor is, the stronger the signal we need to stimulate that sensory receptor. For example, we have free nerve endings, and these free nerve endings are going to aid us with pain, heat, and cold. We also have Merkel discs. And Merkel discs are located directly beneath the stratum basale of the epidermis, and they aid us with light touch. So if somebody's tickling you with a feather, they are stimulating your Merkel discs. Then we also have, on the other end of the spectrum, we have peniasin corpuscles, which have many layers of protective tissue around them, and they are embedded deep down in the dermis. Those peniasin corpuscles are going to be for deep pressure. If you've ever had a bug crawling across your arm or your leg, tickling your hairs, the tickling sensation associated with hair is when you're stimulating the sensory receptor in the hair root plexus, or the root of the hair plexus. So, let's go back to this concept check question. Which kind of sensory receptor can convey the most kinds of information? We have free nerve endings, Merkel discs, the hair of the root hair plexus, or we have the Cutaneous corpuscle.
Sorry to interrupt. I think I left a pair of sunglasses in this.
Come on and grab them.
I'm so sorry. They'd probably be there. I think Jean left after me. It was during my math class in the afternoon. So.
Just come on up and look and grab them.
Thank you very much.
So, guys, gals, back to the concept check question. What kind of sensory receptor conveys the most kinds of information? The kinds of information we talked about are heat, pain, cold, and pressure.
Thank you.
That's correct, Ashley. Free nerve endings. The free nerve endings are capable of taking heat, cold, or pain and conveying those three kinds of information. And then Merkel discs, hair root plexi, and Cutaneous corpuscles all convey variations of pressure as the kind of information that stimulates them.